Hello, this is Miss Moore, and today during chemistry we're going to discuss the strength of acids and bases. Today's essential question: what determines the strength of an acid or base? Okay, our first topic is acid strength and ionization, or what is the relationship between acid strength and ionization. So here we go. So here is the definition of acid strength. The strength of an acid is defined by the equilibrium position of its dissociation or ionization reaction. What? Okay, let me explain what all of that means. Here is an ionization reaction. So we're starting with HA, aqueous, and what this H and A is H would be like the H1 plus ion, and A is some anion. And aqueous because it's dissolved in water. What that results in is H3O, or hydronium ion. And remember, that's a measure of acidity. And the anion floating along by itself. So this is an equilibrium reaction of an ionization reaction. Well, that didn't sound very good. So what is meant by the strength of an acid is defined by the equilibrium position of its dissociation or ionization reaction. Well, let's talk about that next. Okay. Let me erase these equilibrium arrows. And what we mean by equilibrium position is the arrows, how far forward or how far reverse this goes. So we could have arrows that are the reaction goes pretty much mostly forward and only a little bit backwards. We could have something where the reaction is fairly equal forwards and backwards, or possibly a reaction where it's mostly backwards and only a little bit forwards. Okay, and so these are equilibrium positions. So this one, the equilibrium is very far to the right, or the products are very much favored. This one, the products nor reactants are really favored, and in this lower one here, the reactants are very much favored. So for a strong acid, the equilibrium lies far to the right, which means if you were to mix with a strong acid, if you were to mix this acid in water, you would end up with a reaction that is very favored to the product direction, and very few go back to the reactant direction, which means you're going to end up with a whole lot of hydronium and free anion and very little of your original acid. Okay, so for a strong acid, you're going to end up with a lot of product and very little reactant. In fact, for a strong acid, the equilibrium or the amount of dissociation is somewhere very close to 100%, meaning just about 100% of the original acid is dissociated or dissolved in water. Okay, so for a strong acid, this means that there's going to be a very high hydronium concentration after dissolved in water and a very low acid concentration, your original acid concentration. For a weak acid, the equilibrium concentration possibly would be about equally favoring the reactants and products, but truthfully, often the equilibrium position favors the reactants with only about a 10% dissociation, meaning that 90% of the acid stays together, or you have only about 10% of the solution being hydronium. Okay, and again, that's for a weak acid. Also, most acids are weak acids. Okay, so what are some things that influence ionization, or the degree at which an acid, this HA, breaks apart in the presence of water? All right, so the strength of the HA bonds, remember the hydrogen with some anion, helps determine the degree of ionization. And remember, the strength of a bond often has to do with electronegativity differences. Electronegativity differences between the H and the bonding anion. Okay, so the stronger the bond between hydrogen and its anion will lead to less ionization energy, because that anion is holding the hydrogen very tightly. Okay, while a weaker hydrogen anion bond will lead to greater ionization. So the acid strength is inversely proportional to the H anion bond strength. So again, the stronger the bond between the hydrogen and its anion, the weaker the acid, because the anion doesn't want to release the hydrogen during ionization. Okay, so the strength of the strength of hydrogen anion bonds are the most important factor influencing the strength of an acid when comparing atoms in the same group. So if we take, for example, the halogens, so we've got fluorine, chlorine, bromine, iodine, etc. Remember that electronegativity going down a group decreases because of the addition of energy levels, okay, which means going down a group, the bond strength decreases, which means what for the strength of the acid? Going down a group, the strength of the acid acid strength will increase. Okay, so again, as you're going down a group, electronegativity decreases, which means the bond strength decreases, leading to an increased acid strength. So again, acid strength is inversely proportional to bond strength. Bond polarity also helps determine the degree of ionization, which is a measure of acid strength. So when the hydrogen anion bonds with greater polarity will ionize more than a less polar hydrogen anion bond. Okay. So in a polar molecule, the shared electron is closer to the anion. Okay, remember, a polar molecule means that there's a larger difference in electronegativity. So the anion is actually holding the electron that they're sharing closer to itself. Okay, so the hydrogen is not being held quite so tightly. So the polarity of hydrogen anion bonds are the most important factor influencing the strength of an acid when comparing atoms across the same period. Okay? Okay, so if we were to look at a portion of a period of the periodic table, let's take, for example, silicon, phosphorus, and sulfur, going across the group, electronegativity out of room. So electronegativity increases, right? Which means when bonding with hydrogen, sulfur, or I guess we say going across the same group, polarity of the H anion bond is also going to increase. Which means the electrons being less and less fairly or equally shared, which means ionization increases, which means acid strength will also increase as you go across a period. On to strong and weak acids. Let's start by saying that most acids are weak, only partially ionizing in water. Okay, there are 6 common strong acids, and they are HClO4 or perchloric acid, HI or hydriodic acid, HBr or hydrobromic acid, HCl or hydrochloric acid, and H2SO4, sulfuric acid, and last, HNO3 or nitric acid. You need to know these 6 acids. Very, very important. Make sure you know these. And you can assume all other acids are weak. Some degree of weak. Okay? So again, HClO4, HIB, HBr, HCl, H2SO4, and HNO3. Make sure you know those. Okay? Strong acids, so strong acids end up with weak conjugate bases. And that's because the relatively low electronegativity of the anion, which makes the HA bond weaker, which is the reason the acid is strong, also results in the conjugate base being less attracted to the proton, making it weak. So the reverse is also true. Weak acids have strong conjugate bases. So going back to the strong acid and base, because the anion so readily releases its H, once the anion is there, it's, by itself, on the product side, it's not overly attracted to that H. For weak acids, it's the other way around. The acid the anion is more reluctant to release its H and is very happy to gain it back. Hopefully that makes sense. Okay, last topic, strong and weak bases. Like strong acids, strong bases completely ionize in water. Group 1 and 2 hydroxides are considered strong bases. So that means hydroxide, remember, is OH, and group 1 would be like lithium, sodium, potassium. Group 2 would be like, beryllium, magnesium, calcium. So I guess we should have our pluses here, right? So any of these connected to an OH is considered a strong base. Lithium hydroxide, sodium hydroxide, potassium hydroxide, whatever. And also like acids, if you have a strong base, your conjugate acid is going to be weak. And if you have a weak base, the conjugate acid will be strong. And that's it for today. Have a good one.